All right, so I do want to talk to you guys a little bit about this now. We will go over it again later, but this is called the Maxwell-Boltzmann distribution. I'm going to misspell this probably, I'm very sorry. Boltzmann, something like this, distribution. And we use this for a couple different scenarios, but we'll talk about this in depth later. But for now, kinetic energy is on this axis. And on this axis is the number of particles. Okay, so say at a low kinetic energy, I have a certain number of particles, at a different energy, I have a different number of particles. This would have more particles than this one would. All right, so what happens is when we have a sample, it always kind of follows the same curve. It makes them kind of like this. Like a nice little jump. What this is saying is that we have a lot of particles, we have a little particles moving slow, a lot of them are kind of average, and then some of them are moving faster. Because not all of our atoms move at the same speed. They're always moving at a bunch of different speeds. So here's the average right here in the middle. And this peak, the average kinetic energy is related to the temperature. So if I raise or lower the temperature, if I raise the temperature, they have higher kinetic energy. And if I lower the temperature, they have lower kinetic energy. In the context of this demo, though, we are really concerned with there's a barrier. Molecules need a certain amount of energy to react, right? We said they have to collide with enough energy, and then the last piece is the orientation. Okay, so the barrier is showing us where the molecules have enough energy and where they don't, because this is tracking their kinetic energy. So molecules that have enough kinetic energy will be able to do the reaction, even if they don't always do the reaction because of the orientation, but they have enough energy to do the reaction. And the particles that don't reach that barrier, that don't have enough kinetic energy, they can't do the reaction. So depending on the reaction, this line might be different places in here. And if I increase the temperature, my curve will change. But what's interesting is that when we increase the temperature, the curve gets like this, like it's spread out more and lower. And if I decrease the temperature, we get a curve that is like this. Okay, the reason why the curve goes up and down is because if our sample stays the same, the area under this curve also has to stay the same. Because the area under the curve is the total amount of all the particles. When things are slower, the max temperature is lower, and so they're all kind of squished together. But when the temperature is really high, like in this green line, we still have particles that are the lowest temperature, but now our highest one is further, so it gets spread out. So I call this the melting ice cream cone graph sometimes, because the hotter it is, the lower it gets, like its ice cream cone is melting. So we'll go over this again in class, so don't worry too much right now, but you should keep in mind there is this energy barrier for reactions, and only the molecules that have enough kinetic energy, like the ones over here, would be the ones that can react.